The goal of this presentation is to talk about the pharmacokinetics of SSRIs and the impact of marijuana on the rate of metabolism. According to the New York Times and National Institute of Drug Abuse, the amount of college students using SSRIs has grown as well as the students using marijuana. So what is the relevance of this to physics? Well, pharmacokinetics is mixed with concepts of motion and energy, and the process of neurotransmission requires energy or action potentials. Additionally, the rate of metabolism involves the motion of molecules undergoing chemical transformations, and enzymes act as catalysts, and the rate of reactions can be influenced by these. CBD or THC increases the SSRI's concentration via the CYP2D6 enzyme. This inhibition of the CYP2D6 means that the reaction is not being catalyzed well, leading to a higher amount of energy that is needed and therefore work that needs to be done in order to convert the antidepressants to their inactive form. This project aims to explore marijuana and CBD impact on SSRI's metabolism. And another question to consider is, how does marijuana affect metabolism in Michaelis-Menten equation? This figure is from a research article that will be mentioned later in this presentation, but basically both CBD and THC inhibit CYP2C19, decreasing the metabolism of CYP2C19 substrates, including sertraline and escitalopram, therefore delaying the production of active metabolites. THC and CBD have also an inhibition effect on CYP2D6, affecting their ability of these drugs to be converted into their inactive form. The effects of inhibition are shown by the thickness of the lines in this figure. This model is similar to the homework problems about the neutrophil in that we cannot accurately depict the situation in a system schema because the system essentially is changing due to evolving drug states. In this case, the SSRI would only have contact with the CYP2D6 enzyme in the system with the SSRI present, and the CBD/THC and SSRI present system would have the CBD/THC competing against the SSRI in order to bind to the same enzyme, so they would be competitive inhibitors. Ultimately, if the CBD or THC inhibits the CYP2D6, there's going to be a larger activation energy needed in order for the reaction to occur, and for SSRIs to bind to CYP2D6 to convert to their inactive form, therefore requiring a larger activation energy as seen from the Gibbs free energy plot. Additionally, a velocity curve for the reaction can be made as this larger amount of energy needed for the reaction to occur means that there's going to be a longer half-life because these molecules will not be able to be metabolized by enzymes as quickly, so there would be a decrease in the velocity or rate. According to this derivation, as the concentration of the competitive inhibitor increases, the denominator in the equation becomes larger due to the term 1 plus I over Ki. This results in a higher effect of Km, making it more difficult for the substrate to bind to the enzyme. Therefore, the competitive inhibitor reduces the apparent affinity of the enzyme for its substrate. This would then increase the maximum velocity overall. This is a model of the Michaelis-Menten graph modeled using Jupyter, and you can see that as the concentration increases, the reaction rate increases until a terminal velocity is reached. I use pseudo data, but as you can see, the data models Michaelis-Menten equation pretty well. With the value that should be 20, there is a velocity in the pseudo data of 20.24 approximately. Also using Jupyter, I modeled Brownian motion without a competitive inhibitor, and I also model it with a competitive inhibitor. And since Brownian motion is motion of random movement, both non-competitive and competitive inhibitors influence the random motion, but they do so in different ways or mechanisms, with the non-competitive inhibitor inducing structural changes in the enzyme that affects its catalytic activity, with competitive inhibitors directly competing with the substrate for the active site instead. The competition for the same binding site may lead to a more ordered or selective interaction during collisions, which may explain the trend seen in these graphs with the competitive inhibitor having a generally less random movement, as seen by the less intense ups and downs. And although there's not much research going into the impact of marijuana on SSRI metabolism, there's an article that discusses the impact of escitalopram and sertraline concentrations by using previously estimated pharmacokinetic parameters and standard dosing regimens for an adolescent CYP2C19 normal metabolizer. This research was primarily done by Samuel E. Vaughan, as well as others, and as seen from this figure, the half-life can be shown to increase for sertraline and escitalopram, with the total body clearance being reduced to 25%. So overall, physics that were discussed in this presentation, there are enzymatic reactions and activation energy. So obviously energy, it's related to work, and then Brownian motion and molecular collisions, as well as Michaelis-Menten kinetics. And the inhibition of CYP450 enzymes by cannabinoids resulted in a higher activation energy for the metabolism of SSRIs. This increase in activation energy led to a slower reaction rate, prolonging the half-life of SSRIs. This could be dangerous, as people taking these drugs daily could potentially end up overdosing. The Michaelis-Menten kinetics model captured the relationship between substrate concentration and reaction rates. And then the derivation showed that because higher substrate concentrations are required to achieve half maximal velocity, when competitive inhibitors are available. This would also lead to an increase in the Michaelis constant Km.